Sign on, please. Okay, you can sign on. That commits not. I am. You can't see the screen though. You see that? I don't see it. So what am I doing wrong? Oh, maybe it's the wrong. I know what it is. That works. Come on, dude. What? That works. Okay, so let's go over number 5. Read that for yourself. So again, you might want to, it's up to you, but you might want to write out these questions before you do the solution in your notes, and then you can use it. It's more easy to review that way. You can just cover the solution when you're reviewing. So it says the ball is rolled up. After 3.6 seconds, it reaches a maximum displacement. So the idea is this. It starts with some initial velocity. We don't know what that is. That's what we're going to find. And, okay, so we got the distance. Let's make a list. VI, we don't know. The time it takes to go up, we know, is 3.6. The distance, usually, this isn't given. Well, I just turn it off, guys. Thanks. 2.6 goes up the slope. That's considered positive. Okay. Now, the key thing to pick up on is that it mentions the ball reaches some maximum height, some maximum displacement. Whenever something's rolling up a hill and it reaches a maximum displacement, at the point, at the maximum distance, its final speed at that point is 0. it's going to turn around. And unless something stops it, it's going to reach that point and then head back down. Whenever something, it doesn't matter whether we're talking upslope or, I can circle, this would be cool. Doesn't matter whether I'm referring to something that's, oh, that doesn't work. I thought I could turn it. Doesn't matter whether I'm referring to something that's going up a hill or even sideways, if it's moving like this. Whenever something turns around, the point where it turns around at, its velocity is 0 at that point. Because it's going from a positive, let's say it's got a positive, just before it turns around, let's say it's got a positive velocity of 1. On the other end, where it's turned around, it's got a velocity of -1. Right? And what do you have to pass through to go from 1 to -1? You have to pass through 0. So any turning point velocity is 0 at that point. So we're going to call this the final point at the top. So that's my VF. VF is 0. So that's your list. You want to solve for this. I would, surprisingly, we're going to use this equation, which, like I said earlier, last lesson, it's not used that often. But this is the one that fits for this problem. So just divide both sides by t. Whatever you do on the right, you have to do on the left. Okay, and then I would multiply both sides by 2. I'll do it in yellow. Whoa. Hello. What happened? Okay. Multiply the right side by 2, multiply the left side by 2. Cancels out here. So you can see, I mean, it's helpful to know how to rearrange these equations in advance. And then subtract VF from both sides. Okay, and then just plug in. And the time is 3.6. Minus VF, VF is 0. So what's that? 5.2 over 3.6. It's a little, what, 2.5-ish? No. I estimated wrong. So it's 1.4. It's positive because it's going up. We take moving upwards is positive. Six. So like I said, it's not a bad idea. Look at the, I've given you the full solution. For you guys, now that you know what the best method to review is, I would write out the question. A little extra work, but when it comes to review at the end of the week, just cover the solution, right? And go through it step by step. See if you can solve the problem. Have it right in front of you. If you just want to have the handout, I guess you've already, okay, what am I thinking here? I guess you could do it on the handout, fine. You've got enough room, for sure. Do it that way. Just make sure you cover the solution when you're reviewing it. Okay, so read number 6 to yourself. So it's doing this. Right. That's the ground. And it's moving up. It's slowing down. Reaching some point, and then it's turning around. And then it reaches 5 meters, I think it says, above the ground. Yeah. So, what is the velocity at that point? So what is the velocity there at that point? So we know what the initial velocity is. Initial velocity is 10. That's plus 10, right? Okay. So let's make a list. We know initial. We know what the acceleration, we talked about this last day. If something's moving up, negative velocity or negative acceleration in either direction. It's always negative 9.81. We know what the displacement is. It's measured from here, from this point to this point. So the point of it's measured to, this is the final point. Final point's above. So it's a positive displacement. If the final point's above where you start, it's positive displacement. Okay, and then it's asking us for the final velocity right here. What is that? That's my final point. What's the final velocity? So that's your list. So choose from the 4 equations. That's the equation. So I would, in this case, it's easy. You don't have to rearrange, but I would practice rearranging this equation. The first 3 at least, well, the 3 main ones I talked about. Practice rearranging it. So solve for D in this case. Practice solving for A. So this is a little easier. We don't have to rearrange. Just plug in. That's 10. That's negative 9.81. And that's positive 5. Well, let me do this in my head. So this is 20 times 5 is 100 plus 100, 200. All right.
Please excuse the interruption, Mr. Kionia. Could you please post your attendance?
Yep.
Thanks.
Forgot to press the button. Done. So square root of 200. What is that? 6. I don't even know. Square root of 200 must be about 14. Let's see, what have I got? Oh, I forgot to subtract that in my head. My estimate was wrong because it's 100 minus some smaller number. So that works out to be actually 1.4. And it's moving down, right? On the way, if you look at the diagram, at this final point here, moving down, so it's going to have a negative velocity. When you take the square root, because you're going to have VF is equal to the square root of all this. Oops. When you take the square root, you're going to have 2 options, positive or negative. So it's moving down, so it's going to be negative. Now notice I made an estimate. I made a mistake when I estimated it. But that's a good idea to try to estimate. What I forgot to do is subtract. I forgot the negative sign here. So it's 100 minus some smaller number. It's like 100 minus 98 point something. And that's why you still end up with some positive number under the root. But it is a good idea to estimate. And then if it doesn't check out when you plug it into your calculator, then go back and do it again. Okay, number 7. Make a list. So notice it says here, regarding the distance, it says it's up the incline, so it's positive. Up the incline, we're going to call up the incline as positive. Moving up the incline or position up the incline is positive. What's the velocity this time? Okay. So we'll call that the final point sometime later. Okay, they seem to be making use of this equation a lot. Anyways, that equation contains all 4. But we've got to solve for the VF. I would go back to, I already actually rearranged way back here, right? We got this. So I already rearranged it up to that point. That was in, what was it? Question 5. I want to solve, in this case, I want to solve for the VF. Oh. So you can just plug in your values. You've got D is 2.8. And your time is 1.5. And your initial velocity is 2. So what's this? 5.6 divided by 1.5. I don't know. 3.5, 1.5. Yeah. So it's, I said 1.5. It's actually 1.7. And it's positive. So it's still moving up. Positive means it's still moving up. It hasn't turned around yet. Number 8. It looks kind of similar. Let me just check here. Similar to 6, but it's asking for the initial velocity. And let's just, I'm going to just copy the diagram here. Change it. Okay, so a couple things I got to change here. The object's displacement, it's still 5, so that's checked. That's the same. Time, so displacement is 5. Time is 3 seconds. Initial velocity, that's what I don't know. That's what's different. So that's an unknown. And acceleration, whether it's moving up or down, it's always 9.81 negative. So which equation do you think I should use? Given this list, which equation do you think I should use? You think this works, maybe? Yeah. Except I want to solve for this. Can you see the purple, or is that just too dark? Okay. Good enough? Okay. So subtract this from both sides. Whatever I do on the right, I have to do on the left. Oops. That gives me the term that contains the VI. Okay, and then when you're dividing, remember, put a line under the whole expression. You don't just put a line here, put a line under the whole expression. Okay, so this is an expression here. Expression contains two or more terms. And divide by the t. Okay, and then just plug in. So you got 5. Nine times 10, 90, 45. Something not making sense. Oh, that's right. Positive. So 9. I'm trying to do it in my head here. 45, 50 divided by 3, about 16. Yeah, 16.4. So I would round. You can keep it either 2 or 3 sig figs. 16 or 16.4. Okay, and again, notice I tried to estimate it. Do that and then check your answer. It's a good way to do it. Can't always. Sometimes if you got trig functions, it gets a little difficult. But okay, just make a list. So ball rolled up. What do you know about the acceleration? Just because it's moving uphill. What's it limited by? Yeah, so it has to be, how'd you express it in terms of 9.8? You know the value has to be what with respect to 9.8? So it mentions here the ball is rolling down. That means the velocity must be negative. Negative. We know the acceleration has to be less than gravity. Can't be greater than 9.8 because gravity is what's causing this to eventually move down it rolls up and then it rolls down. Gravity is what's causing it to move down, and the incline dilutes the gravity. So whatever that acceleration is, it's going to be less than gravity. So use this equation. Okay, and then solve for acceleration. You should know how to do that for this. Make sure you get the signs right. So if it's moving down, it's a negative. And initial velocity is 2.2. And the time is 2. So that's 2.4. It's about 1.6. Negative 1.6. Oh, there's it. 9. Okay. So I estimated I was off a little, but it's less than 9.8 as expected. Absolute value is less than 9.8. It has to be negative because it's pulling on the ball, slowing it down on the way up. Okay. Okay, I need my coffee fix. And Mr. Chessel's giving me free coffee. So you take a little mini break, that's fine. I'll be back in a second. Be right back.
I understand like the temperature and all that stuff, but we're having like a review session with Mr. Zhang after school today. So like hopefully we can fix that.
Good.
How's the coffee?
That's great, man. I'm going for Chelsea coffee every time now. Better than the staff room.
What makes it so much better?
I think it's because it's more freshly brewed.
Oh yeah.
I mean, usually the staff room coffee is good, but for whatever reason, just the beginning of the year, it's kind of had an aftertaste. So I don't know. Maybe it's because it's not fresh beans, right? Left over the summer. But this is, Mr. Chestnut can buy whatever coffee you want, pay less. Charges 50 cents here. Oh, go ahead.
Yeah.
Okay. Yep. Go on here. Crap, did I print the wrong stuff? No, I didn't. Good. You guys studied addition of vectors last year, like representing vectors as an arrow, adding them tip to tail. Yeah, I mean, I'm going to go over it regardless. I just like to know. So let's take a look. First of all, let's title this addition of vectors. So define what a vector is, what a scalar is, and give me examples. So a vector is a quantity. What do I mean by quantity? Some measurable quantity, right? Or even a vector, not necessarily measurable, but something that you can calculate. So it's a quantity. Yeah. Yeah. That has both magnitude and direction. So examples of that. The easiest one is displacement, right? Displacement is like distance. You could think of it as distance with a direction. So each of these have most of them have their synonymous scalar or analogous scalar. Displacement, velocity, the speed with a direction. They're exactly the same magnitude with each other as long as you're moving in one, as long as you don't turn around. Speed and velocity, same magnitude. But velocity will have a direction, positive, negative, or east-west. Acceleration, force, momentum. What else? Anyone add to that? Impulse. Later on, you haven't studied these yet, but electric field, magnetic field. So that's important to know because that means you can represent all of these vectors here with arrows that you can add tip to tail. That's an important point. All the rules I'm going to just summarize for you next can be applied to any vector. Can't be applied to scalar. So what's a scalar? Quantity. It's a quantity. Sometimes it's measurable, sometimes it's not. Magnitude. What does magnitude mean? Just a number. That's what it's a fancy word for number. So what are examples? Time. Well, let me just, you know what? Just so it's more related to the one above. Distance, right? Related to displacement. Same magnitude as displacement as long as you don't turn around. Keep moving in a straight line. Displacement and distance have the same magnitude, but displacement will have a direction. Like I said earlier, right, left, east, west. Distance, no direction, just some number. Speed. Okay. Time. Mass. Density. Although density can be a vector sometimes. Yeah, you can turn it into a vector. What else? Charge. That's a symbol for charge, Q. Yeah, we could add, there's more that we'll add to the list as we go along. Those are just some examples. So the point is that a scalar cannot be represented with an arrow. Only vectors. Okay. So what do we know about, let's see here. Maybe I should give you an example. We like working with displacement vectors. They're the easiest to start with. So add, let's look at this example. Add two displacement vectors. Okay. 74 or 73 meters north. Sometimes we put little, you don't have to, but sometimes we put little square brackets around it. And 62 meters east. Okay, let's see if you can remember how to, you don't have to draw them to scale, just roughly draw them. Obviously, the north vector is going to be longer, but draw them out. Let's see if you can remember how to add them. Okay. So I'm going to draw north, obviously, just to remind you. North is up the page, south is down the page. East is to the right. West is to the left. Okay. Now, yes, I know we usually prescribe negative to be west and south to be negative as well, but we won't worry about that. We're just interested in drawing the arrows in the right direction and adding them up. How do you add them? Okay, so this is the northerly direction. This is the north vector. That's the 73 meter one. And this is the easterly, the 60. It's not quite as long. It's a little shorter. That's 62. Point towards east. Now that's separated. We need to join them together. Well, I can cheat. You can't. I can do this and then just move it over. Like that. That's how you join. Join the vectors tip to tail. Join the arrows tip to tail. However, whatever type of vector it is, this rule always, that's the first rule. Join the arrows representing the vectors. Tip to tail. Okay? So you're representing these vectors visually, graphically is another way of saying it. That's the first rule. You're going to add them graphically. Okay, the second rule is draw the resultant. The resultant is one vector that you can represent the other 2 or 3 vectors with. That one vector I'm going to draw as a red vector. Oh, no, red. Okay, you're going to draw it from, I'm going to draw the, that doesn't look good. You see that? Yeah. You start at the tail of the first vector. And then you end at the tip of the last vector. So it looks like this. That's your resultant. That's not that clear, is it? Okay, good enough. That's your DR. So here's the rule. Draw the resultant from the tail of the first vector. This is the first vector here. From the tail of the first vector to the tip of the last. So the tip of the last. To the tip of the last. That's the tip, that's the last vector. It's a second vector in this case. There could be 3 or 4 vectors. So whatever the tip of the last, very last vector is, that's where you connect the tip of the resultant to. So it's backwards for the resultant. The tail matches the tail of the first, and the tip of the resultant matches the tip of the last. I just finished this sentence here. Draw the resultant from the tail of the first vector to the tip of the last vector. Is that red kind of? It's okay. How about this? Let me try something different here. Don't be upset. I'm going to go for yellow. Is that clear? A little better? I'll try to use yellow. I like red, but it doesn't show up that well. Okay, so that's how you draw it. Now, we're not done. You'd have to, first of all, notice, and this won't always be the case, but we like to always simplify to a right angle triangle. So this is, first of all, a right angle triangle. So why does that make it easy for us? Because we know how to find dr. We can use the Pythagorean theorem. Dr squared is 73 squared plus 62 squared. And that's the first point. We like to work with right angle triangles because we can easily calculate the hypotenuse. So dr dr is that. Dr works out to be equal to 96. That's the magnitude. Now, here's the problem. Remember, it's a vector, so we have to include direction as well. How do you include direction in this case? It's not pointed to the right, it's not pointed to the left, so you can't say positive or negative. It's two-dimensional. It's on a plane. So when we're dealing with vectors on a plane, we have to deal with angles. Put the angle at the tail. That's the rule. Not at the tip. Put it at the tail of the resultant. You want to write that down. That's the general rule. Put the angle you're going to define it with at the tail of the resultant. Okay? Now I'm going to just go over a few rules for you so you remember. You haven't had this before. This, I'm just going to draw that instead of a fat yellow line, the resultant will be just a skinny yellow line. Saves me time. The angle here, how do we define it? Well, this obviously is north. Okay, this direction is east. You always look at the first thing you look at when you define the angle. This is the way I do it. You might come up with a better way of describing it, but this is the way I do it. You always look at, let me clarify this. Look at that. Look at the non-resultant line in this case, or arrow. It's a white line, right? That white line points north. That is not the resultant. That's what you're using to define the angle with. So always choose the white arrow, the non-resultant arrow. That helps define the angle. So the angle is, we don't know what the angle is yet. We're just going to call it theta. Theta of what? Whatever that white arrow is, that defines what comes second. We're going to have some statement that says something of north. Okay. Define that second direction by whatever the direction of the white arrow is. In this case, up, north. Okay. Now, we always define the direction in terms of to. Can't just say north. We have to say something of north. So the first direction here is defined by the direction that the yellow arrow is leaning. Is it leaning to the east or is it leaning to the west? It's leaning to the east, so we write east of north. Theta degrees. We'll come back to we'll figure out the angle later. Let's just look at a couple of other examples. So let's say we have that's our resultant here. Let's say this is our angle here. How would you define that? Let's see if you can get it. Don't tell me. Let's write it down. Let's see if you can get it. Something of something. Always mention two directions. It'll be a combination of east and north, west and north, east of south, west of south. I always start with this, the white arrow. I look at what the direction of the non-resultant arrow is. In this case, it's the same thing as above, north. That's something of north. Which way is the yellow resultant pointed? Which way is it leaning? East or west? West. That's west of north. Okay, let's try this. I'm just going to try something. I'm trying to get used to this thing here. Duplicate. Okay. You should be able to rotate this, man. Copy. Can you rotate? No? Stupid. I thought you could rotate it. Okay, whatever. I'll redraw. I'm just getting lazy. Okay. So let's do this. Where do I draw the angle? What's the rule? Draw the angle where? At the tail. Always at the tail of the resultant. Tail of the yellow arrow. Okay, so now define it. It's theta degrees, something of something. They'll always have two terms. Okay, so the direction of the white arrow is south. And which way is the yellow arrow leaning? Yeah, west. So it's west is south. Okay, try a couple more. Yellow is always, I mean, I like drawing it as a different color. Just be aware which one is the resultant. It's a yellow arrow. There's the angle at the tail. Define that. Something of something. Theta degrees. Which way is the white arrow? East, west? East, good. So which way is the yellow arrow leaning? Yeah, north of east. One more. How did you find that? East? White arrow is east. What about the resultant? Which way is it pointed? Which way is it leaning? Down or up? Leaning down, right? Which is south. Okay, so you need to know that. Now, back to this. Whoa, it gets really skinny if I do that. That's cool. Okay. Back to this angle. We still need to know what this angle is here. How do you think we can find that? It's a right angle triangle. Now you can apply it. That's why we like right angle triangles, because you know the math for it. I'll remind you, you're going to use a trig function. Which function do you think you can use? SOHCAHTOA. That's another hint. What does that mean? An acronym. Stands for? Yeah, sine, cosine, tangent. So there's three main functions that we usually stick with for right angle triangles. So which one do you think will help us to find the angle? Here's your other hint. What side is this? What would you characterize that in respect to the angle? Opposite, adjacent, hypotenuse? Here's the angle, right? The angle's here. That side is opposite. So that's opposite. Okay, what about this side here? What would you call that? Hypotenuse, adjacent? Adjacent, good. Okay, so which trig function contains opposite and adjacent? You gotta memorize it. TOA, tangent. So tangent of angle is the opposite over adjacent. I don't have enough room here, but I'll get lazy and copy it. I'll put it down here. Okay, tan is that. In this particular case, tan of the angle is opposite. What's the opposite side? 62. Right? That's the opposite. Adjacent is 73. What do you get for the angle? What do you get, guys? Give that a try. 50, 40, 60. One of those. Let's see here. Yeah. Wait. I got. Let's see here. Let's see if they did it right. What'd you get? Put it in degree mode. Make sure it's in degree mode. What do you get? 40, 50, 60, which one? Should be 40. I'm going to do that myself here. Make sure your calculator is in degree mode. Yeah, it should be 40 degrees. We're going to round to 2 sig figs. Okay, am I done? Can I just say 40? Is that enough? What do you think? Would you leave it like that? After I went over all this, what would you add, tack on to the end of 40? East of north, south of north, west of north. Perfect. Now you're done. So it's this. I would circle it because you're nice to Mr. C. Mr. Kionia, I'm trying to be nice. I'm going to circle my answer. That's my answer. Magnitude and angle. Magnitude and direction. Do you know how to deal with, let's say you had this. So that's right, two vectors at a right angle. Let's say you had one that was north. So that's north. I'm making these numbers up. Let's say 10 meters north and 12 meters south. How would you deal with that? How would you add them? You take this and you'd move it in place. So see that little pink line? You move them in place so that the tip and the tail are connected. That's how you'd add it. Now, how do you draw the resultant? What's the rule for the resultant? Draw it from the tail of the first to the tip of the last. That's your resultant. That's your DR. Now, this actually is easier because they're parallel to each other. So DR, you don't have to use Pythagorean theorem because they're not at a right angle. So what do you think DR is equal to? What's the length of DR? How big do you think DR is? 12. Do I add the 10 or subtract it? Good. 2 meters. And which direction? You always have to include a direction. You don't have to put two terms because it's, in this case, it's pointed down. You only need one term. North, south, east, west?
South.
Good. Done. You can put squares around the south if you want. You don't have to. So if the vectors, if the two white arrows are parallel, side by side, you only need one direction, north, south, or east and west. If it's at an angle, you end up with a result in an angle, then you need two terms, east to north. Okay, I got a hand up for you. Do 1 to 6 on page 63, 64. Okay, and I'll post the recording of this later. So what do you